So yesterday, it was a sort of like a random walk through well, just a little bit of everything, right? A little bit of a history of randomness. My sort of like a narrative line was to take you from randomness to quantum and give some kind of a broad landscape of quantum information science, quantum computing, mostly, how we go from describing randomness in terms of probability theory, Kolmogorov approach, and how quantum enters this, and how we use complex numbers, and managed to throw in some interesting characters like Girolamo Cardano and others, right? So today I'm going to still use slides, and it's still going to be kind of a fun lecture rather than anything where we just go into the equation subscript and superscript level. So it's going to be a story about, today I'm going to stress more communication aspects. So yesterday was mostly about computation, how should we sort of have a broad view of quantum computing, and today is sort of going in the direction of crypto. So I would like to tell you a story how investigations of foundations of quantum physics sort of nicely merged with people interested in security. So it'll be a little bit of a history, and I hope it's going to be again fun to look at. So I will start with I'll give you sort of like the outline of people's desire to set up perfect cryptographic system, how to communicate with perfect security, how people did it over time, what were the main trends. And then we'll talk about, of course, the key problem, the key distribution thing, and then how quantum physics comes to rescue, and a few other ideas there. So essentially, as I said, there's going to be two narratives here. One was curiosity-driven research. So that was when people tried to understand what really this new physical theory, quantum theory, that was, as we know, was cooked up about 100 years ago. What is it really about? What are the implications? Is it in particular one thing that dominated discussion at the time was, is it complete? And that was Einstein thing. Is it really the real thing, or is it the first approximation to something deeper and more profound? So therefore Einstein worried about the completeness of quantum theory, and then we have the whole narrative of people trying to understand this. Will take us later to John Bell, who kind of tried to answer this question in terms of more, in sort of more concrete way, and sort of trying to propose experiment where this can happen. And then it will go to experiments, and as you know, that resulted in Nobel Prize in 2022. So there was one line of research, but that surprisingly merged with another line of research, completely different at the very beginning, when people were interested in the notion of security. So we can go to ancient Greeks and talk about how people wanted to protect information then, and then how people moved on, and with the sophisticated technology, people still try to protect information because it was of value. And like 50 years ago or earlier than that, it was just completely two different fields. There was just no overlap whatsoever between people working on the foundations of quantum theory and people working on cryptography. And then those things changed slowly. So one development was Stephen Wiesner, who came up with the idea of conjugate coding. Then Charlie Bennett and Gilles Brassard had the idea how to use this uncertainty principle to encode information in such a way that it may be used for the key distribution. And then in my work on the Bell inequality and quantum crypto sort of managed to bring the two branches together, and then sort of they started feeding each other in a very nice way. That, for example, people working on the Bell inequality side had to now look into certain problems, like, for example, certain loopholes, which were optional when you talk about nature, but not so optional when you take adversarial scenario and think, oh, okay, we are not talking about how nature behaves, but maybe we are talking about how your adversary behaves. So this we will talk a little bit. So this is like the overview of what's going to come in the next hour and a half or so. So I think if it is okay with you, I will just go maybe for 1 hour plus without break, unless you want me to just do 45 plus something. But maybe it's easier just if we just have 1 hour plus, and we'll see how it goes. Okay, so let me start with a brief overview of crypto, how people encrypted and protected information at many years ago. So essentially, when you look at the origin of cryptography, we more or less go to the origin of human writing and the way people started using symbols to communicate with each other. So when you have a finite set of symbols, and I stress finite because here we are in Asia, where you have a slightly different way or different set of symbols to communicate. So it's but when you sort of stick to, say, 35, the Roman alphabet or a Greek alphabet or whatever Phoenicians sort of came up with, a finite set of symbols used to communicate messages, then it's very easy to play with those symbols, to distort those messages, to protect them. So what you can do, you can permute characters in your message, right? So you just place the symbols in a different location, or you can also do the substitution. You can take one symbol and substitute another symbol for that symbol. So that is the two techniques, permutation and substitutions, were used as early as 400 BC, or in the early days of the Roman Republic. Well, Julius Caesar took it from the Republic to the Roman Empire. But so we have those two things. And it's interesting there's still among historians of science, there's interesting debate. Why was it that, for example, the Chinese didn't develop such a system earlier? And most likely it is related to the fact that the number of the Chinese character was huge, and to come up with a method for substitution and permutation was difficult. So the ancient Chinese cryptography relied mostly on, well, actually, there wasn't as such, but it relied mostly on protecting information, relied on hiding messages in some clever mechanical devices rather than playing with those characters. So the first device we know that was used for cryptographic purposes, and it was used in ancient Greece, in Sparta, was called skytale. So skytale was a wooden button of a certain diameter, and then you have two guys. You have two military commander, and they would have wooden buttons of the same diameter. So if you want to send a message if one commander, military commander, wants to send a message to the other one, would take a strip of parchment, would just wrap it around this wooden button, and then you write your message lengthwise. So say, attack tomorrow. And then you unwrap it. So when you unwrap it, it's just, the location of the letters is somewhat different, modulo the rotation of those letters. But letter A is letter A, letter T is still letter T, but the placement is different. And you give this parchment to a courier that takes it to a military commander at some other location. So the other guy gets the parchments, takes a wooden button that is of the same diameter as the other one, wrap it around, and the message would reappear. So that's the first example of first historical record that we have of using mechanical devices, simplistic devices like this for secure communication. So that was about 400 BC. Another method that allegedly was used by Julius Caesar, so we are talking about 50 BC here, was based on substitution. So you take your alphabet, so letters from the alphabet, say Roman alphabet, and you shift the whole alphabet by, say, 3 characters to the left. So A, B, and C are sticking out here, as you can see, and you append them to the end of this alphabet. So then you have a substitution rule, which essentially says, let's see whether this works, yeah, which says for A, substitute D, for B, substitute E, for C, substitute F, and so on and so forth. So you take the same message that we saw before, attack tomorrow, and now we are not replacing we are not sort of shifting the placement of the characters, but what we are doing here, we are replacing one character with another character. So that's a very, very simple substitution method. Apparently was used by Julius Caesar to communicate with his military commander. So the two methods that you saw, well, not so much different. You may say that they all rely on sort of like taking a mapping from, if you look at the substitution, so substitution in a way is a permutation as a map, right? So you take the whole alphabet and you map it. It's a one-to-one mapping to the alphabet. And the sort of shifting the whole by 3 characters is a very simple one, but there could be many, many of them. But of course, you know, if you have to agree on the rule, what kind of substitution we are going to use, then it's good to take a simple one so that you can explain to military commander, I'm going to communicate with you using substitution cipher, and the rule is shift all the characters by, say, 3 or 5 or 42, or maybe not 42 because I'm not. But the number of substitution nonetheless is huge, and it's interesting that it took people a while to have a systematic method of breaking this, and to the best of our knowledge, the first person who managed to crack substitution ciphers was a philosopher of the Arabs, a guy by the name of Al-Kindi, who lived in the 9th century in what is today Baghdad, essentially. But this was sort of like the Persian and Arabic golden age of science. And so he was one of those who belonged to this house of wisdom and so on and so forth. So he was the one that figured out that something that is almost obvious to us, right? That a natural language is not, or be it written or spoken, but a natural language is not a random set of characters. That characters appear with a certain natural frequencies in any single language. So if you take English, for example, you can see here the frequency chart of English language here. So if you take a text, a typical text in English, and look how often a given letter appears. So it's not that they appear with the same frequency. So you'll find that the letter E is the most frequent one. In most Indo-European languages, in fact, the letter E is the most common one. And then certain pairs of letters appear quite frequently. So in English, TH is a common combination, right? So a simple statistical analysis is enough to break substitution ciphers. So if you're given a piece of text, right, and you look and you know that it was encrypted, so to speak, with a substitution cipher, so there was a one-to-one substitution. So what you do, you look for the most frequent character. You find the most frequent character, most likely it's the letter E. So you try, it's the letter E, and then you look for the second most frequent character, and the pairs of letters, and so on and so forth. And you know, the language is very redundant, so you see the message sort of almost popping up immediately. You can fill the gaps very easily later. So that is when you use a typical set of text and messages. But what is interesting, as a sort of a side remark, I couldn't help just to give you this example. I always find it amusing. Some writers are very proud of the skills of the command of language, right? And then there is a genre that is called lipograms. Lipograms are pieces of text where you distort this frequency on purpose. So for example, if you read this first paragraph, it's written without the letter E, the most frequent character in English. And the most famous lipogram in the history was written by the French guy, Georges Perec. As it happens in French, the letter E is also the most frequent one. And so he managed to write the whole book called La Disparition, without the letter E. And it's, you know, it's 85,000 words, really amazing. So you can just read this book and it's mind-boggling. And what is even more mind-boggling, that it was translated to English and was also translated in a way that avoid the letter E. Of course, Georges Perec shouldn't put his name on the book, right? And then there was a weird German guy, a poet, who he had obsessive dislike for the letter R. Not only he was writing his poetry without the letter R, but for something, so he wrote 130 poems in German without the letter R, but he also tried to avoid it from the daily conversation, so you can imagine. So today, of course, except lipograms, when we talk about one-to-one substitution, it's quite clear that they're kind of simplistic, right? So simple frequency analysis and you're done. So one-to-one substitution is not even considered today as an encryption. It's just change of the alphabet. You just take something and you substitute something else for it. So it was recognized, not, you know, after Al-Kindi, people realized that one-to-one is not the way to go. So the next step in the history of encryption was one-to-many, right? So if one-to-one doesn't work, so they're called monoalphabetic cipher, that way you have one-to-one substitution for one alphabet, another alphabet. Here you have a polyalphabetic cipher, so that means one alphabet and you try to make different substitution as you go on in your encryption. So that came, and again, you know, historians, if you were to believe historians, they have all kind of different answers. Who did it first? It's not entirely clear. The idea popped up somewhere in 15th century or so, at the end of the 15th century, early 16th century in Europe. Somewhere in Italy, Renaissance was the time there were lots of intrigues and plots and all kind of things, so that one person who is attributed to with inventing those polyalphabetic cipher is Leone Battista Alberti. You may know him as a famous architect and a true Renaissance guy, but other contenders are Johannes Trithemius and Blaise de Vignières. Anyway, let's take Alberti. Alberti at least is credited with coming up with another mechanical device that was poised to revolutionize the whole cryptography later on. So he came up with what is called Alberti's disk. So that disk, which you can see here, is, so you have actually two concentric disks, and on the perimeter of the disk, you write the alphabet, the letters from the alphabet, on the inner and the outer disk. And the relative rotation of the two disks gives you the substitution rule. So that's a simple shift, right? So you can shift it by 3, 4, 5, whatever. And then as you go along, so for example, if you want to encrypt the message, you can use a sequence of substitutions. So you can certainly, for example, if I want to send a message to Bill, I can agree with him that, you know, I use encryption in which I will encrypt with a sequence of substitutions, which I define as 7, 14, 19. So I shift the alphabet by 7 characters for the first letter. I use another substitution. I shift the alphabet by 14 characters for the second letter. And then I shift it by 19 characters for the third letter. For the fourth letter, I go back to the first substitution. That's 7, 14, 19, and I keep on repeating. So every third letter is encrypted with the same shift, right? So what I need to communicate to Bill is, of course, the sequence. I said 7, 14, 19, and Bill remembers this, and this is our cryptographic key, so to speak. So he knows how to decrypt. And Alberti's disk, of course, you can do it without Alberti disk, but it was a useful device where you do all those shifts and you simply just write your cipher. So this this had some advantage that sometimes, you know, like in monoalphabetic ciphers, the reason why it's very easy to use statistical analysis, that the mapping of a given letter, so a given letter is always substituted by the same character. So for example, if you have the letter L, in monoalphabetic cipher, it will be always something and will not change. Whether here, with this kind of substitution, if you have a plain text cell, you have two letters L next to each other, they will be mapped into different characters. So that makes the whole statistical analysis much more difficult. But not, you know, again, if it is a short key, if it's just only, if you use only three substitutions, then it's not that difficult to break it. And the person who is credited with breaking polyalphabetic cipher is Charles Babbage. You know, again, a very interesting character from the, you know, in the early 19th century, he managed to work out, among many other things, he was working, as you probably know, on the first analytical engine, the sort of, he was a pioneer of computing, but he was also interested in breaking ciphers. So as you can see, it actually took people a while to break polyalphabetic ciphers in systematic way, a few centuries, right? And then the concept of Alberti disk actually picked up. And when we had sort of more complicated electromechanical machines, the Alberti's disk was sort of put together and evolved into a rotor. So you have several Alberti's disk on one rod, and then you can implement more and more complicated polyalphabetic ciphers. So the more sort of substitutions you have, the more difficult it is to break it. And as probably most of you know the story, the most famous machine probably of this type was designed by a Dutch engineer, Artur Ekert. It was called Enigma. And Enigma was used during World War II. And what was another spectacular thing, it was simply broken by Polish cryptologists led by Marian Rejewski, who shortly before the outbreak of World War II, the Poles managed to read essentially all German communication. It didn't help them that much to be you know, at the end of the day. And but the work that started in Poland continued in the United Kingdom and Bletchley with some further development, and that was actually quite essential for finishing or sort of like winning the war on the Allied side. So the Poles who broke Enigma are sort of one of those who managed. It was a very spectacular way of implementing or applying some ideas from permutation, from the group theory to break those ciphers. So it's very nice. I usually like when I give lectures to illustrate in group theory. So it's very nice to illustrate with the way Rejewski in particular, but also the two other guys managed to. They were just mathematicians, right? So then they use all those tools they had to break Enigma, and it's a beautiful illustration how mathematics can actually help in real situation. So when you see this evolution, right, when we go from Scytally to Alberti disk to Enigma, the moral of the story is, okay, there are many clever inventions like monoalphabetic ciphers, polyalphabetic ciphers. Then you have Enigma, that is like super polyalphabetic cipher. But every single time there's an ingenious device or ingenious method for encryption, there's an ingenious method for breaking the cipher. So the question is there a way to design something that cannot be broken? So that was like the problem in crypto, right? And the answer is actually yes. So if you take the polyalphabetic cipher to the limit, so for each character, you have a different substitution. So that's the limit. So then you end up with something that is called a one-time pad. And one-time pad, probably the easiest way to explain it is maybe not as a limit for polyalphabetic cipher, but as sort of a simple encryption of binary sequences. So you take a message that you have, you use ASCII code or whatever, turn it into binary. So we change the alphabet, write your message in binary. And then we have those two characters, our two protagonists in quantum information for sure, in quantum cryptography in particular. We have Alice and Bob, usually two good guys who want to communicate, and they have some secrets to share. And in order to do that, they're going to use one-time pad. And one-time pad relies on the fact that Alice and Bob met and managed to establish a random sequence of zeros and one, which is identical. So they have identical, they share identical, truly random and secret sequence of zeros and one. And that's called a cryptographic key. So that's written in red characters here. So then they go into two distant locations, and whenever they want to, whenever one of them, say Alice, wants to send a message to Bob, what she can do, she can take the message, write it in binary, and do bit-by-bit addition to the key, right? So the bit-by-bit addition is just like a regular addition, apart from the fact that 1 + 1 becomes 0. So then by adding, so you can see it on this side, so one-time pad, you take the message, take the key, generate the cryptogram. So the cryptogram, because the key is truly random, like if it is randomly generated, the message is not. The message has the pattern of a natural language. We know that, right? So now you add those two, and the randomness from the key is translated to the cryptogram. So the cryptogram is truly random. If the key is random, this randomness sort of transfers to the cryptogram. So the cryptogram, if you look at it, then doesn't have any pattern because it inherited randomness from the key. So then you send this message over any unprotected channel, and frequency analysis and statistical analysis doesn't work because any pattern, natural pattern from a natural language is completely wiped out at this point. So you have just a random string of characters unless you have the key. So Bob is here, the cryptogram arrives, Bob takes the key, and he's subtracting this randomness from cryptogram and recovering the message with the same binary addition. So this scheme here, which was proposed in the 30s and 20s, was shown to be absolutely secure as long as certain conditions are satisfied. So the conditions are that the key is truly random, is truly secret, so it's only known to Alice and Bob. It's as long as the message, so you cannot just use part of the key and reuse it again. And the key is never used again, so you only use it once, so that's why it's called one-time pad. You use it once, it's gone, right? If you start using it again, so you're going into sort of like a polyalphabetic cipher regime where things are not entirely secure. In fact, there are very good examples in the history of cryptology where, in particular, the Russians after the war and the Soviets tried to, they had some issues with they used one-time pad and they reused the keys in several occasions, and American exploited this. So there was a whole program called Venoma that managed to decrypt the so-called one-time pads where certain assumptions regarding the key management were not satisfied. But anyway, so Shannon managed to prove in the 1930s that this kind of system is absolutely secure. There is a perfect cipher. You cannot break it as long as those assumptions are satisfied. So what's the problem? So you know what the problem is. The problem is that somehow we made this assumption that Alice and Bob have the key, and it's one-time pad. We also said we use it once, the key is gone. We cannot reuse the key again. So there's a need for the key distribution. So here we come to crypto. The big problem is, okay, fine, we can have a perfect cipher as long as we can solve the key distribution problem. And so what kind of solutions do we have today to the key distribution problem? So one come under the label public key cryptosystems. I'm not going to talk about it. It's a fascinating as a topic from the series of lectures, I would say. But the idea that mathematicians came up in the 1970s or so was that maybe we can avoid the key distribution as long as we can somehow introduce two keys. One of them is public, one of them is private, and base the whole security not on what they call information security, where there's not enough information to break the system, but on computational complexity. I talked about computational complexity yesterday. So the fact that there are certain mathematical problems that relate to the two keys, and essentially the security there relies on the difficulty of performing certain computational tasks. So the public key cryptosystems is not really a way of fixing the key distribution problem, but it's sort of like avoiding this in a very elegant mathematical way. It's not known to be, it's not provably secure, because many of those results in, as we talked yesterday, in computational complexity cannot be, or we don't have any proofs. There are certain assumptions that there are certain complexity classes and there are certain relations between those complexity classes. But nonetheless, they work, and but still, we know that some of them may not work when we have quantum technologies. So because of, again, those complexity classes, for example, if you take factoring, it's difficult for classical computers, but it's not difficult for quantum computers. So it belongs to this class BQP that we talked about yesterday. And therefore, once we have a quantum computer of sufficient computational power, we will be able to break those ciphers. So then we have some issues with public key cryptosystems, and therefore today there is an effort to establish a set of new public key cryptosystem going beyond RSA, going beyond those that depend in their security on say factoring or discrete log, and looking for another mathematical problems which are difficult even for quantum computers. So the idea is, okay, maybe it will take some time to build quantum computers, but let's be prepared and let's use conventional classical methods, but make those methods resilient to quantum attacks in the future. It's very difficult to do that. In fact, there is an Americans establish a certain set of standards. There are certain mathematical problems based on vectors, on lattices, and so on and so forth. We will not go into this, but it's possible. But to prove security is extremely difficult, and it's not entirely clear whether those that were proposed will be secure in years to come. But certainly they have an enormous advantage that they're very flexible in zillions of applications, and we can implement them essentially now without even quantum technology, hoping that they will be resilient to quantum technologies in the future. So that's sort of one way to avoid key distribution problem. The other way is to fix it, trying to fix it. And this is actually what quantum crypto is trying to do. So quantum cryptography basically says, well, we find a way of distributing the key, and that way works even if we have quantum computers. So quantum crypto is secure even against quantum attack. The problem here is, of course, that it requires quantum technology and may not be good for all computational tasks. There's a variety, the whole spectrum of cryptographic or information protection scenarios. So usually quantum crypto is used for point-to-point communication, but a few others as well. But certainly is not as flexible as something that we can do with public key cryptosystems. But nonetheless, this is what we are going to talk about. So every now and then I drop some topics, so I decided to insert a slide for you saying, okay, it's your homework, I'm not going to talk about it, but it's interesting, so take a look at this. So I encourage you to look at public key cryptosystem, RSA, elliptic curves, and lattice-based. Lattice-based are interesting because because they have proposed as sort of a new generation of cryptographic systems that's supposed to be resilient against quantum attack. And it's a growing controversy. You know that shortly after Peter Shaw published his paper on quantum factoring, I think maybe 2 or 3 years later, I don't remember, he had another paper where he claimed that the lattice-based crypto is not secure. So there was an attack on lattice-based. That paper, Oleg Regev showed is not correct, so it was withdrawn. But then there were a few other papers, and even last year there was a very interesting paper from our Chinese colleagues showing that lattice-based crypto can be broken on a quantum computer. Again, it took, but it took all community all over the world about 3 months to figure out where is the mistake. There was a mistake, so it doesn't work. But it's sort of like makes you, if you're into this, if you enter this business, would you put your money on lattice-based crypto? If you every now and then you see how close it is, and it's coming closer and closer to come up with a quantum algorithm that may eventually break lattice-based crypto. So it's interesting to see this, and I don't know whether lattice-based crypto will survive for a long time. Yes, please.
And they can fix the line. So
they can
fix the line of the mistake in the
the Chinese?
Yeah.
Well, I wish them good luck. That would be a breakthrough.
I don't think that there's still like a mistake in the one.
Mm-hmm. Well, I communicated with that person from Tsinghua who came up with this algorithm. He was a young guy, he came up with a very nice paper that took us about 3 months to figure out the mistake. Thomas Vidig was the first one who actually pointed out where the mistake was. And then it's interesting that I like this young researcher because, he was very unhappy that this mistake was found, but he was also very honest about it. He posted on the website that there is a problem here, and then I said, well, look, you should talk about this algorithm anyway, because it doesn't matter that it doesn't work. It just shows that you use a set of interesting techniques and tools, and maybe eventually something will come up. But he went into sort of like he decided to disconnect for a while and work hard on fixing this problem. So if he fixed that, it would be great, but I think that would be a real breakthrough. So it requires a certain degree of scrutiny. Say again, sorry.
I wrote the new paper that.
Oh, yeah?
I don't know, I haven't read the paper yet.
Oh, you say the Danish guy? Yeah, the Ivan. Well, he's a very serious and well-established cryptologist. Okay, well, look, guys. So there's something else to look at. Look and find a mistake. Okay, that's the homework for you. Or don't. So by the end of the school, you'll be judged on your on your prowess.
So Arthur, you want him to do it in an afternoon or in 2 days, and it took you 3 months?
Yeah, well, that's it took me sort of like it was not even. It probably would took me longer. Thomas Vidig was the one who found it in 3 months, right? But now there's a new one coming up. So there's Ivan is he's very accomplished, well-established Danish cryptologist. So if he says so, it should be taken very seriously. But okay, if lattice crypto is dead, I don't mind, Anyway, so this area is known sometimes as I don't like this name, but it's called post-quantum crypto. I don't know why. So the area where you use current mathematical techniques to defend yourself against quantum attack. It's probably quantum resilient would be more appropriate, but never mind. So this post-quantum managed to stick. And so there are many interesting papers that in this field, and to what extent that people can really come up with quantum resilient thing is an open question. So going back to the key distribution. So when we have this simple one-time path scenario, the key is it's the key distribution problem. It's not that the computer scientists do not have a set of tools to do something about it. So for example, one thing is, as long as you can establish how much any third party, like an eavesdropper, Eve, can know about the key, computer scientists actually have a good set of tools to extract the secret key. So if I somehow know that Bill knows a fraction of my key, and I know how many bits roughly, or at least I can put a bound on it, then I can extract a shorter key that Bill knows nothing about. So, but the problem is that finding how much Bill may know is difficult for me, because he's a clever guy and he has all kind of clever tools to his disposal. So how do I know how much he learned during the key distribution that I had with my friend? So Bill was listening very carefully, and I really don't know. What is the signature of Bill's eavesdropping in my data? So that's a very difficult thing to establish. In fact, it's impossible. However, once you sort of know the bound, there are those randomness extractors, there's a privacy amplification, there is a set of tools that I can use. So just to give you an example how it works. So suppose I have the key of 2 bits. So just take a very simplistic case. I have 2 bits, call them x1 and x2. And I know that somehow Bill managed to learn 1 bit. But I don't know whether it's x1 or x2, and maybe he knows some, I don't know which one. But I know that it's not more than 1 bit. For some reason I learned, somehow I managed to figure this out. So one thing I can do the binary addition. I can add x1 to x2 and get 1 bit. But I know that this 1 bit is secret, that Bill doesn't know this bit, because he knows at most 1 bit, x1 or x2, so he certainly doesn't know. For him, one of them is completely random. And by doing this binary addition, I get just 1 bit that looks random to him. So this is a way that, I had partially secure binary string, in this case of length 2, and by binary addition, I managed to generate a shorter, in this case, 1 bit binary string, but I know that it's entirely secret. So you can extend this kind of idea in a slightly more sophisticated way works, but you see the crucial piece of information here was that I managed to put an upper bound on Bill's information on my key. If he knows 2 bits, then I cannot do anything about it. He just knows the key. But putting an upper bound gives you a chance. So computer scientists know, so the key distribution doesn't have to be perfect. There could be errors there could be some partial leak. As long as we can make some estimates, then it's fine. We can actually extract secret keys using all kind of set of tools. And so the figure of merit that we usually use here in cryptographic scenario is the mean entropy. So as you know, there are many entropies that you can come up. There's a common one is, of course, the Shannon entropy. But when you're looking for the worst case scenario, and so we take the probability of guessing. So if I want to estimate, so my apologies, Bill, I'm going to use you as my educational tool for a while. So I refer to you. You're dedicated to science and education, I know. So if Bill, so how do I estimate in mathematical terms Bill's information about my key? So one thing you can use is if you can estimate something called probability of guessing the key. So that is, what is the probability that Bill can actually guess my secret? And then what you do, you take log base 2 minus log of this probability of guessing, and that's what is called mean entropy, or we call it the conditional mean entropy condition, you know, entropy of my key condition upon his knowledge. So this mean entropy is a figure of merit that is important because that tells you roughly that if I can estimate this mean entropy, that tells you roughly how much key I can extract, how much secret key I can extract from something that is not entirely secret. So we are really after this figure of merit. Actually, it will get more complicated if you really want to go into this. We can talk about smooth conventional mean entropy and so on and so forth. But in the first sort of approximation, think about it this way. Probability of guessing, take minus log of that gives you mean entropy. And this number is important because it tells you how much secret stuff I can get out of something that may be partially secret. So that's sort of quantified in a classical scenario into something that is called the leftover hash lemma. I just like the name, you know, I don't know who came up with this, but so where you just, if I have the raw key, which is partially secret, so this is this gray stuff here, and I managed to estimate the mean entropy, so how much a potential adversary may know, or what is sort of like uncertainty. So the mean entropy, to be more exact, sort of quantifies Bill's uncertainty about the key. So then I can use a set of mathematical tools to shrink the whole thing and extract the key. We may or may not go to this on Thursday when I talk, but this is just to give you a rough idea how it works. So let me add to your homework. So apart from, so you can maybe look up why cryptographers use mean entropy rather than Shannon entropy. So think about it or look it up. And if you're more ambitious, you can try to go further, define security using Kolmogorov trace distance between probability distributions. I may or may not talk about it on Thursday. We'll see how it goes, but that's related. If you have more appetite to learn about how computer scientists can extract data from something that is partially secret to something that is almost secret, just you can look it up. So we managed to pin down the problem, right? How we can have a pretty good, almost perfect cipher using, for example, one-time part. As long as in the key distribution process, as long as we are able to estimate how much information leaked out. In classical scenario, you may analyze different channels that say Bill can eavesdrop on me. You may say, oh, this guy is clever. He has this technology. He has another technology. This allows him to learn this. This allows him to learn that. But at the end of the day, you really don't know how clever he is. He could be pretty clever and he can have technology you never heard of. So there's no fundamental, so, well, that may be the case, right? So the thing is that there's also, in classical physics, there's no law that protects him from sort of a passive eavesdropping without leaving any traces whatsoever. So he may even have such a technology that he can read the whole key, and I'm not aware of this because he's not leaving any traces of his eavesdropping. So in the classical domain, there's no way you can estimate, at least at the fundamental level, you can estimate this mean entropy. So I will never be in a position to know for sure how much Bill knows. So then, then we move to quantum entanglement. That probably is not your homework. I'm sure you know about it, but that's sort of like I'm sort of slowly moving to the other narrative. So let's summarize the crypto part. So I was telling you about this one-time part that was essentially sort of invented in 1918 by this guy Gilles Vernem. Then public key cryptosystems. There's an interesting story here, by the way. They were first discovered by a bunch of researchers working for the British GCHQ. The GCHQ stands for the Government Communication Headquarters, and that's the bunch of mathematicians and researchers who work for the British government to protect the security of communication, but also it's about eavesdropping on anyone else and the usual stuff, right? But they had a wonderful tradition and a bunch of mathematicians working there and a bunch of misfits as well. And one of them was this person called James Ellis, who was half a mathematician, half a poet and a geek, and you know, one of those guys. Sometimes you wonder what he's doing, you know, right? And he came up with this idea, but not in a very mathematical terms, of public key cryptosystems. So it's a little bit like, you know, sort of a kind of having a safe box where you can, you have two keys. One is for locking the safe box, another one is unlocking the safe box. And you can say, I give everyone open safe box with a locking key, but I keep the unlocking key. So once you lock the box with the locking key, the so-called public key, you cannot unlock it with the same one. You have to use the private key to unlock the safe box. So he had this kind of idea, but it had to be sort of taken further by some mathematicians like Phil Cox who actually came up with the mathematical systems. So they were discovered originally at the GCHQ, but those guys couldn't publish it. So I felt always very sorry for my colleagues from GCHQ because they have good ideas, but sometimes, you know, they are not paid that well. But and they also don't have this, you know, the vanity factor is also suffering because they cannot just advertise their work to the rest of the world. But you know, now we know that they did it. But at the time, without people, our American colleagues from like Rivers, Edelman, and Shamir, who discovered about maybe 2 or 3 years later, they came up with a very similar, actually identical ideas. So it's interesting to see, even though those people didn't communicate, it's interesting that the development in the field comes to a certain point where certain ideas are bound to emerge, right? So, and they really popped up. So then I talk a little bit about, we are coming into sort of quantum part. But let me sort of now go to the other narrative, and then I'm going to merge those two narratives, maybe not today, we'll see how it goes. So in parallel, there was an interesting development among physicists who try to understand how nature works. And we'll come to the key distribution, and we'll see how it eventually comes to the key distribution. So the big thing, of course, the big mystery in the early days of quantum physics was why we cannot make precise predictions. So how is it that identical preparations lead to different outcomes? So if you take this very, very simple experiment where you take a single photon and it's impinging on a beam splitter, and it's either reflected if you put a photodetector there, or transmitted if you put another photodetector. So one of the two detectors will click, right? But you cannot predict which one. So you can have identical preparations. You have in this Platonic, at least, sort of view of this experiment, take a zillion of those experiments, the same momentum, the same frequency, the same placing, everything is the same. And you know, here goes the experiment, and the outcomes can be different. So Einstein couldn't actually digest this. He said, look, this doesn't make sense, right? So how come this is happening? Most likely, because the quantum theory, by the way, tells you that the initial system, the initial preparation, the initial state are identical. But then Einstein says, well, most likely, at least I believe that this is not the case, that there is a better description of quantum state, that there are certain variables that are not incorporated into the quantum descriptions. And once you know those variables, those extra quantities that describe the state, then you should be able to make predictions. So then it's not random, it's not inherently random, but it is sort of it looks to us like this because we don't know those hidden variables, so to speak. Once you can see those, when you know those variables, when you have a theory that allows you to interpret them in a proper way, that the outcomes will be perfectly predictable. So you would know what's going to happen in this case. So that was a big dilemma. So Einstein considered quantum theory not to be complete. So he wrote this paper with Podolsky and Rosen in 1935 under the title, "Can quantum mechanical description of physical reality be considered complete?" And sort of he posed the question, right? The title is the question, and his answer was most likely not. And he had an argument there showing that a nicely constructed algorithm showing that arguments showing that most likely that's not the case, that we have to work harder. So Einstein was not against quantum theory. He was for it, but he thought the work is not finished yet. He said, we have to work harder. It's just like we are halfway through. We have quantum theory, but it has some bizarre features, and I'm not taking this. You guys have to work harder and come up with more complete. And once we have this more complete theory, then everything will be predictable. So I just want maybe to move to, and then this sort of idea was taken, most people treated this 1935 paper as a very kind of philosophical paper, because Einstein didn't come up with any sort of way that you can possibly verify this worldview, that this is not complete in experimental terms. So, for most physicists, if you cannot come up with something that you can verify or refute, then it's just a philosophy. You can, maybe it's true, maybe it's not true, who knows, you can talk about it, but that's as much as you can do about it. So the big achievement, and by the way, most physicists were not so much interested about this. Quantum physics was working, quantum physics was fine, it was making statistical predictions, and they were good enough, explaining many things, so that was as good as it gets. But there were a few people who were curious about this question posed by Einstein, and one of them was John Bell, who John Bell was from Northern Ireland. He was working in Geneva at CERN, and his job was essentially to design accelerator. And this is a very good example that sometimes maybe you shouldn't be doing what you're doing, but and after hours, so he was doing quantum foundations. And so this picture, I'm told, Alain Aspect tells me that this picture was taken during his discussion with John Bell. And John Bell came up with a way of actually refuting the concept of Einstein's local hidden variables. So he said, well, actually, no, maybe it's a testable proposition. Maybe what Einstein had in mind can be resolved by experiments. So in fact, John Bell started by trying to come up with the theory of hidden variables. So he was taking Einstein's science. He was saying, okay, well, let's try work it out, how it can work. And he realized that there were two components. If you want to have those hidden variables local, so to speak, so if what's going to happen here only depends on things locally, it doesn't depend on some spatially separated region, so then you have to give something. Either you can probably construct hidden variable theorem, but it's going to be non-local, or you can have, if you want to have things local, there's inherent randomness somehow involved. So then he worked harder, and then he managed to show that you can refute, there are ways to refute, at least there are ways to refute experimentally local hidden variables. So probably by now you all know about Bell theorem, and there are different versions of it, of course. The most popular one is this CHSH, Clauser-Horn, Holt-Shimony. CHSH, John Clauser, I think was Holt. You look at that, okay. So I know that C is certainly for Clauser. The first H is probably for Holt. Then S is for Abner-Shimony, and the last one probably for Michael Horn, but I'm not sure. Anyway, so CHSH is a version of Bell inequalities. And there are many ways, of course, of showing, proving, looking at it, but probably like if you look for one slide and one liner, is that you consider a situation where you have two observers, of course, Alice and Bob. You put them into two different locations. You put a source of entangled particles in between, and you may want to measure certain not compatible properties of those two particles. So you have, say, one photon from the source going to Alice, another photon from the source going to Bob, and say you're going to measure different types of polarization of this photon. And if it is indeed the case that each photon is then carrying a well-defined polarization, right? So that the measurement that you are going to take is not going to make this polarization happen in some mysterious way, but is going to uncover the polarization that already exists. So there is, for every single type of polarization, there is a value of it. And working with this assumption, we can just simply say that if Alice, for example, is measuring polarization A1, she can get two different values, +1 and -1, in some units of H bar. And those values do exist prior to the measurement. And if she's going to measure another type of polarization, say A2, then again, this polarization also has a well-defined values prior to the measurement. And then the same for Bob. You assume that B1 and B2 have well-defined values. The experiment runs as follows. So you have the source that repeatedly emits photons, and the polarization, each time the photon arrives at Alice's location, she's going to measure either A1 or A2, choosing randomly between the two. And the same for Bob. Bob is going to choose either B1 and B2. Now, if you take this sort of like a local realism view, you say that those values do exist. You know, they are predetermined values. And if this is the case, you can construct a different, you can think then about A1, A2, B1, B2 as random variables, having values, taking values +1 and -2. And then you can construct another random variable S, which is a linear combination of those. And you can look at it. So here this, it's A1, and we have the term B1 plus B2 here, and here we have term B1 minus B2. So if it is the case that we have values +1, -1 associated with those random variables, A1, A2, B1, B2, and you look at this expression, and you can see that in this case, in every single realization of this experiment, those values, all four values exist, right? You may not be measuring all of them, but they do exist. Then one term in here has to be equal to 0, and the other one to ±2, right? So if B1 and B2 are identical, both +1 or both -1, this term is 0, and this term is equal ±2, and vice versa. So in any case, we can see that S can only take two values, +2 and -2, under those assumptions, right? And if you run this experiment many, many times, then the estimated average is going to be somewhere between -2 and 2. And that's essentially CHSH inequality. So starting with the simple assumptions that those those values are there, even though, prior to the measurement, you come up with inequality that you can see here. And that's not exactly, if you then repeat the whole argument using quantum physics, we don't have, there are many ways of doing this, we don't have to go into this. If you say, for example, I put a source of entangled photons, I prepare them in a certain state, and I measure the polarization, then I use a different physical theory. So on one hand, the previous argument was we were using the description that was purely classical. We are using the assumptions that those values do exist, that there are local hidden variables, and that led us to this inequality. If you take quantum mechanical description of the world, then you can see that this figure of merit, the estimated average, may not be confined to the interval -2, 2. It may actually go outside, and it can go all the way up to square root of 2. Today, when we talk about, so this is actually an old-fashioned way of talking about Bell inequalities or CHS inequalities. Today, and I may take this view, it's kind of interesting and maybe more productive and nicer in many applications to think about what is called CHSH game, where you consider those two different boxes in two different locations, and you translate the whole scenario into Alice and Bob having devices, and those devices can act either according to local hidden variable theorems, where there is a set of instructions telling each box how to behave in every single round, and then Alice and Bob can choose randomly inputs to the boxes, and boxes would respond with some outputs. And then looking at something of the conditional probability distribution of outputs depending to inputs, you can classify those probability distributions into those conforming to local hidden variable theorems and those that are not conforming to them. So we'll take this line when I talk about Bell inequalities, but let me skip it. But if you look at this class of conditional probability distributions, then you can divide them into classes. You say there are certain types of correlations that can be really explained in terms of the local hidden variables. That is sort of the Einstein world, and that would be this sort of a classical square in the middle. All those sets that can be, mathematically shown in a rather precise way. The sort of a set of those probability distributions that are represented in higher dimensional, sort of like in the case that I'm describing, you need a space of at least 8-dimensional real space. You describe by a point, that what we call probability points. So that there are convex sets of classical correlations. But what is interesting here, of course, in our description is that the set of classical correlations is actually a subset, is a strict subset of the larger set of quantum correlations that are predicted by quantum mechanical description. So, and then there's even a larger set of what we call non-signaling correlation that respect relativity. What is interesting though is, and it's relatively sort of like, not recent, but an interesting observation is that the set of correlation that respect relativity is strictly larger than the quantum set. So quantum physics is somewhat more restrictive. It respects relativity, but it could have respected relativity in a more relaxed way. But it's sort of like, we know about non-signaling correlations, which are not quantum, not physical. So anyway, in this kind of language, the Bell of CHSH inequality says that is a certain function. It says that if I measure those correlations, this figure of merit that I observe can reach the value 2 or is between -2 and 2 and not more. It has to be in this interval. In quantum mechanical description of the world, we allow this figure of merit to go from -2 square root of 2 to 2 square root of 2. So if you observe correlation somewhere here, you refute local hidden variable model, saying that, you know, the world cannot be just explained in terms of local hidden variables. We don't know about the correlations which are outside the quantum. There is, as I said, there's a set of non-signaling correlations. We use them as a mathematical reference point, as an interesting mathematical tool, but we haven't observed this kind of correlations. So I encourage you to look at the CHSH game, but anyway, the moral of the story is then experimentalists moved in, and now the sort of the thing is to check what is the case. And of course, you know, there's a wonderful story of people taking or not taking Bell inequalities seriously. Most people actually didn't. So we have John Bell in the 60s writing about his idea, and nobody really cared that much. And there were few, there were just outliers. And it's, you know, after John Clauser, who did his experiments, there was Alain Aspect. He was probably the first one who managed to sort of like percolate to the attention of most physicists, who said, well, it's interesting, you know, it's good that quantum physics works as sort of equations tell us. But the philosophical part of that was somehow always sort of downplayed. So it was just the case that here we have a rather powerful statement that there is inherent, if you take, you know, if you keep this locality in mind, you think, oh, either there are some weird communication between the particles, there's something truly non-local going on, or there is inherent randomness. So that means that the quantum physics in this sense is complete. That one cannot hope for better description in this beam splitter experiment that I showed you. This sort of description of the state is as good as it gets. You cannot do anything better than that. You have to leave with statistical predictions. And that is actually quite, to anyone who was brought up in a tradition where science explains things, is making predictions, but also makes explanations, that is really weird. It's very difficult to sort of, if you really think about it, it's difficult to comprehend the fact that something just pops out for no reason, right? It just like happens. Where's history to this event? There's no history to this event. It just happens. Okay, so many people can question this view, saying that there are some assumptions, and you know, we divide the world into classical and quantum. Maybe we shouldn't be dividing. So there are ways around. And the philosophers can keep talking. You know, that's not the end of the story. But in the first approximation, this should have been sort of like a shocking news to most physicists at the time, but it wasn't really. So people just mostly ignored it, and nobody cared so much about this thing. The Aspect experiment was kind of noticed, but nobody made a sort of a big hoo-ha out of that. And then, you know, those experiments were, of course, repeated. It was not always the case. After John Clauser, by the way, who showed the violation of Bell inequalities, there were some other experiments that showed that the Bell inequalities were satisfied. So at the time, those experiments were not so precise. So Aspect was maybe the first one who showed that actually almost certainly they are violated, but then a few others came along. So the number of people who contributed to the current state of the art, where we know they are violated, from John Clauser to Alain Aspect to Nicolas Gisin to Anton Zeilinger, Jean-Wei Pan, and two of my heroes who contributed, who worked for the Defense Research Agency. I used to work with John Rarity and Paul Tapster. Those were like, you know, it was a great time. We were doing quantum crypto in a defense research lab in Malvern, not far away from Oxford. And it was absolutely fascinating to see how both difficult and easy and fun it was to do research. First of all, for some historical reason, in the UK, crypto, you know, this lab was under the Ministry of Defense. And believe it or not, Ministry of Defense essentially at the time was not supposed to be working on crypto. Crypto was one, the Foreign Office, and there was another research agency, the GCHQ that I mentioned, that is somewhere else in Cheltenham. And those guys were supposed to be doing crypto, but not people in the defense research lab. But you know, the guy doing crypto, the bunch of computer scientists, mathematicians, having no access to lasers or anything related to something that can be used to violate Bell inequality, which I'll talk in a moment. So it was we were not supposed to be doing this kind of thing. And as John Rarity put it, you know, in our lab, if I don't aim my laser at a tank, I'm not doing a research here. But of course, you know, it was not that bad. And so what I like also was interesting human dynamics between John and Paul. So John was sort of, if you know John Rarity, he's a rather outgoing, and he traveled to meetings and conferences. You've probably never seen Tapster, and for good reason, because Paul Tapster hardly ever left Malvern. So Paul Tapster, his life was essentially confined to 3 points on the map. One was his house, the other one was the lab, and the third one was the bridge club where he worked, you know, he played bridge. Paul hated going to any meetings and conferences, but he is probably one of the best experimentals I ever had the pleasure to work with. This guy had amazing intuition, and he couldn't care less about anything else. So that's Paul Tapster. And so the two of them were great because Paul was very keen to work on the experiment, and John was very keen to travel and tell the world about it. So that brings us to quantum cryptography, and I'm just bringing those two narratives together. But I think that as we are reaching almost 1 hour and a half, maybe I'll stop here just to summarize, and I'll continue on Thursday. But essentially what I tried to do today was this, to tell you that there were two different branches of interesting branches, one related to security, the other one curiosity-driven research related to understanding randomness. And so we went through the history of security or sort of crypto type research from the early days of simple substitution ciphers to one-time paths, and how we ended up with a key distribution problem. So we marked this as a problem. We identified the problem there is to estimate how much our adversaries can possibly know about what we have. And once we have this number, the mean entropy, for example, we can use mathematical tools to extract a secret from that. And we stopped there. And then I switched to curiosity-driven research, where Einstein's unhappiness about quantum theory not being complete led us to recognize at the end of the day that depending how you look at refutation of local hidden variables, but essentially you may take the view that there is inherent randomness in nature, that there's something that nobody knows, nobody can know, nobody can predict. Bill even cannot predict with his superior technology. You know, it's inherently there. Bill cannot, there's no no third party, not even Bill can predict what's going to happen in the beam splitter experiment, whether it's going to go this way and that way. And that's interesting. That is for the first time we have a statement that it's not randomness for whom, it's just randomness, full stop, right? At this point, this event is truly random. And we are coming to the point where we are going to bring together those two things. And you see that they're coming very close together. The key distribution problem, estimating how much randomness or lack of knowledge is there, with a physical statement that there is a truly random thing in nature. Now we just have to bring them together. And that was the origin of quantum cryptography, as came from sort of my side. Of course, Charlie Ben and Gilles Brassard were looking at it from a different perspective with this Heisenberg uncertainty principle. But at the time, we didn't know each other, and also they published. It was all before the internet and before rapid dissemination of work, and their work was published in proceedings of some Indian conference that the proceedings were published only, I don't know, maybe in 100 copies or so. And Gilles was so unhappy about this fact that it was not documented early enough that he decided to take this and have it reprinted. And I think it finally appeared in journal later, much later. So my work was essentially, I didn't know about their work. And it was interesting for me to learn about it at some point when I published the paper, and so in the process of referring the paper, I learned about this work. I was both happy and unhappy at the same time. So the reason I was unhappy, of course, was that, okay, well, someone else had this idea, not so happy about that. But it's interesting thing, you know, when you do those things, and I was not very secure with not very sort of confident that what I'm actually doing makes any sense whatsoever. And if you're a student, a young researcher, you don't have that much confidence in your work, and you don't know whether it's important, not important, maybe rubbish, maybe there's a problem there. So to see that well-established researchers like Charlie Bennett, Gilles Prasad were doing something along those lines was actually a sort of like a boost of morale in some sense. So, but I'll tell you this story on Thursday, and we'll see. I think that it would be good to, if you have any questions that you can send, you want me to elaborate on something, I'm quite happy to go in any direction. I'm happy to go on the whiteboard and do some equations if you have some specific questions, but I don't know, maybe I'll just, at least the first lecture, maybe I'll just go on slide and finish the story I wanted to finish today, but I don't think I will do that today. Anyway, so any questions about what I said today? Yes?
How do we exploit correlations greater than 2 root 2?
How do I exploit?
How do we exploit
to this
correlations greater than 2 root 2?
Oh, greater than 2 root 2, right?
It seems to be a powerful resource. Great.
Yes. So we, it's a very good. So in fact, you know, it's interesting. If you look at mathematical correlations, non-signaling correlations, which are non-signaling but cannot be explained by quantum. So they are sort of, this value of S goes up to 4 for this particular type of correlations. And the way even though it's sort of like a mathematical thing that you can never reach, the CHSH inequality can be viewed as trying to approximate those correlations. So you can see that you can write those correlations if you use a certain mathematical approach, which I can maybe explain next time. You can see that the probability of winning in CHSH game is essentially the overlap of probability distributions that you have with those unrealistic correlations. So this mathematical correlation serves as a sort of like a reference point to you. And the probability of winning CHSH game, if you have those unrealistic correlations, would be 1. But we don't have them. So the question is, if you cannot just win this CHSH game all the time, you could only do it with unrealistic correlations, how well you can perform. And you can show that if you use classical correlations, that the best you can do is to win this game roughly 75%. So up to 3/4 of cases, you can get it right. So 75% is your success rate. If you use quantum correlations, you can go further. You can go something like 86%, but not any further. There's something called serial sum bound, which bounds your performance in quantum thing. And then you would have to have other resources to be able to win this with probability 100%. So having this helped actually to not only to sort of like put a perspective. So this serves as an interesting mathematical reference points for many considerations. And the other thing is that you can also do all kind of easy bounds because the structure of those non-local correlations is somewhat easier than the quantum set. The quantum set of correlations is horrible, even in the simplest possible case. We know it's a convex set. We know it's smooth here, but it has sharp edges there and there. So it's a monster. It lives in, and I'm talking about the simplest possible scenario, the simplest Bell scenario, where we have two binary input, binary outputs, two parties involved. Even in this case, the set of quantum correlations can be sort of placed into a-dimensional real space, and it's convex, but it is complicated. And those cross sections, you can reveal all kind of complexities there. But the set of non-local correlations is actually simpler because it's a polytope, and then you can take all kind of, you can do all kind of bounds by working with those not achievable correlations, but at least they put them, some bounds on what you can achieve in quantum cases. So I think that we gain lots of insight into the nature of the CHSH inequality. Even the CHSH guys, I don't think they had this insight that we have looking at those non-realistic, but nonetheless very useful mathematically correlations. Yes?
We talked about the two-party version, the inequalities there. Are there three-party and eight-party extensions?
Oh, yeah. So the scenario that I was talking here, taking the simplest one is called two scenario. That means like you have two parties, you have two inputs, so the binary input is X and Y, inputs are binary and binary output. But you may consider having n parties, so there are n different individuals, and then they may put inputs that, any number of inputs and consider any number of outputs, finite, but any number of those. So those scenarios are more difficult, but as you can imagine, especially mathematical physicists, they love it, just have something 2, 2, 2, then the first question comes to how about generalizing this, right? So just, so yes, so that's being considered, but the 2, 2, 2 scenario is kind of interesting because it has there are certain things that you can only do in this particular scenario. For example, there's certain dealing with binary observables is kind of special. There's something called Jordan's lemma, which you can show that that is actually quite important when we talk about device-independent crypto. You can show that you don't have to go okay, let me just, so you have this box, right? In this sort of box scenario, there's Alice and Bob, and they have those boxes, and they put inputs, which is a binary input. It's either 0 or 1, and out of the box comes either 0 or 1. And you can just think about the whole thing as having a quantum systems inside, and 0 and 1 is going to choose which observable you are going to measure, and the output, the result of the measurement, just comes as the output from the box. So the fact that those observables have two outputs, but the fact that the system inside could be very complicated. So your observable could be n by n matrix, but has only two outcomes, right? So the eigenvalues are degenerate, +1 or -1. It turns out that you don't have to consider what is inside to be a highly dimensional system. A qubit will be enough. And that's great, because then you can show all kind of interesting simplification in this case. And that's why we like this system. It gives us all kind of interesting stuff. I'm not saying it's not worth investigating more complex scenario. I'm sure there is. Maybe something interesting will come out of that. But we can get such a long mileage out of the simplest 2 scenario, which is why we are studying this. Yes.
I know that recently a number of European security agencies have decided to go for frequency instead of giving other reasons. I was wondering if there's going to be part of some committee or a meeting on this. Second, I was curious if you have any insight on how these methods are secure processes for Europe, as well as in the States, unless East is.
Yeah. So the it's it's an interesting and very interesting and very difficult question to answer in precise terms, because it's a combination of science and policy and politics and sort of even some aspects of social sciences, I would say, and trends and things. So the question is, why should we bother about quantum crypto that requires quantum technologies and it's somewhat limited in its usage at the moment, right? When we can actually look at in the quantum era, we can protect information not with quantum crypto, but with classical tools that are good enough to protect information even against quantum attacks. And the first sort of the first country that took that became proactive was the United States, where there's National Institute of Standards and Technology, and so this agency in the United States is responsible for setting up the standards for future communication, so that it's not good enough to have a good way of doing this. You also want to make some sort of standards that you can sometimes even communicate with your enemy who's using the same kind of a system. And then, so this agency recognized the fact that there is a need for, well, doing something. And having a tradition in setting up standards for communication in public key crypto system, there was a natural extension is to go to community of hardcore cryptologists, people, engineers who know how the security works in a real scenario. And in this community, there's an interesting spectrum of characters. So there are those who we know how those things work in the real world. You mathematicians don't tell us about this nonsense. There's this super pragmatic approach, very dismissive about all this sigmas, deltas, alphas on the whiteboard, right? So there is a merit to this, of course, because there is sometimes, people working on the other side of the spectrum on the theory, they think that they discovered absolutely something fantastic, and they don't realize that if you take it through the hoops of implementations, there are issues at every single stage, and those guys, engineers, have to face those issues, implement them, and they know that the real world is not the platonic world that I was describing here. So there is sort of like interesting spectrum, but it's fair to say that in many of those committees, the hardcore pragmatists dominate, because once they have a good track record, government agencies trust them. They may not be using the most sophisticated tools in the world, but they're effective, they protected things, they have something to show. So that created a really very weird dynamics in the US on the committee. So as you probably know, that the government, that there was a public competition and this is always a good idea, to announce to the world, look, we are collecting ideas for the next generation classical public key crypto systems. So the people started submitting those ideas, and there was a committee that was selecting them. And that was there was an interesting sort of a combination of characters and people and attitudes. And the evaluation process was a bit embarrassing, I have to say, because there were some of the crypto systems that were selected, not to the final stage, but they were sort of shortlisted at some point. And some of them failed in a very spectacular way. So there were at least 2 cases where something that was supposed to be secure against quantum attack was broken on a PC computer in Zurich by someone who works for IBM, and said, okay, well, for the weekend, I just have this challenge. Let me check this system. And so this is embarrassment where you have something that is already shortlisted to be secure against quantum attack. And there's a guy in Zurich who goes on a PC and breaks the system without any quantum technology, right? So that shows that in this kind of community, there was a bit of those who knew about conventional tools knew very little about quantum. Those who knew about quantum probably didn't know about those conventional tools that we did. So that is a generation problem. I think that there's just a lack of education in those fields. And I think, as I said yesterday, I think you guys are in a much better position to judge in the future. So finally, we have a set of standards that the US imposed for post-quantum crypto, mostly featuring lattice-based cryptography. But as I mentioned earlier, this lattice-based, if you ask mathematicians, at least, they're not so sure that they will last for a long period of time. I myself, I'm not sure. I wouldn't put my money on lattice-based, even though I like mathematics. I think it's pretty cool, and I think it may work for a while, but I don't think a long-term this is a solution. Now you ask about the European thing. Europeans usually follow Americans, right? Because there's just, what can we do, there's a big guy there, and then there's not that much we can do about it. So I don't think we will just come with anything. We may have our views and ideas, and sometimes whenever in the past we try to push European solutions, sometimes we failed because we claimed that they were better than Americans, but the American imposed some standards, and unwillingly we had to follow them. But I have to say that on some of those European committees, at least those that I'm familiar with, the same dynamics happen in the US. So I think it's interesting, because it just, sometimes you go as a scientist, you go to a meeting and you'll be surprised how immune people can be to scientific arguments. It's just sometimes other factors decide upon certain things, and just this is sort of goes beyond the point of this lecture, but it's an interesting story. So it's just thanks. Yes.
You mentioned the story of James Ellis, who basically discovered or had inequality.
Yes.
There are similar stories in quantum photography already that we found out later that some kind of secret service already had this.
Not that I mean, if that is the case, it's so secret that nobody knows about it. I don't know. I think that the story, of so far, maybe there's a sort of someone, like some early days of, I think, my life, I went to some quantum optics conferences, and atomic and laser physicists talk about things. I wanted to learn the field. It was interesting for me because I wanted to know the techniques. And it was always fascinating to watch that someone talking about the lasers and something being developed here, and there was always a Russian guy in the audience who said, "Oh, that was invented, long before, somewhere in Novosibirsk or somewhere." So I always had this vision that there was a snow hut in Novosibirsk, that everything that was invented later was invented there before. So whether I'm not trying to, our Russian colleagues for sure, contributed immensely to this field. So I'm not making fun of that, but when you have those sort of geopolitical divisions, it's possible sometimes that something, especially something that is relevant to national security, could be invented earlier. John Ellis is a good example. In quantum crypto, I think it's very unlikely. So the story we have so far is that there is an interesting guy, Steven Wiesner, who is a son of Jeremy Wiesner. Jeremy Wiesner, his father was the head of MIT, and he was like, a very powerful political character. Stephen, in contrast, was just super shy. This guy was absolutely like a bit of a misfit. He had some ideas, and he didn't fit into academic community that well. He ended up, by the way, he passed away a few years ago, sadly, but at some point he left US. He went to Israel, and he was trying to devote the rest of his life to solar energy and so knowing Steve was a real pleasure. And so he would just be calling you sometimes in the middle of the night, asking questions that were completely unrelated to anything, like sometimes about politics, sometimes about something. but extremely shy. So he is the one who had this idea of conjugate coding, and he wrote something about it, but it was neglected, rejected. But when he was a student in New York, he was sharing an apartment with Charlie Bennett. So Charlie Bennett learned from Steve Wiesner about the whole thing, about this conjugate coding, and was sort of talking to people. Charlie likes talking to everyone. So, and Gilles Brassard happened to be one of those who listened to Charlie Bennett, and then Steve Wiesner wrote his sort of idea for conjugate coding was to use Heisenberg uncertainty principle and to generate sequences to authenticate things like, for example, banknotes. But that was unrealistic, and Charlie with Gilles had this idea that, well, you know, it may work for something else. So they adapted Stephen Wiesner's idea for the key distribution. And then they talk about it somewhere in 84, I guess, in Bangalore in India at a conference. So it was, you know, before my time. And then this sort of stayed as the idea that only like maybe, you know, a handful of people in the universe knew about it. In Europe, we didn't know about it at all, I think, at the time. So when I came into this through a different path and a different route, I didn't know about that work until David Deutsch, who was my supervisor, he said, you know what? Charlie Bennett talked to me some time ago, and they were talking about this and this. Maybe it's worth checking. And then it was somehow, when I wrote my paper, it was refereed, it was pointed out that maybe I should actually refer to this idea. It's not entirely new. So then I just realized that then I met Charlie Bennett and I talked to him. So you see, at that time, there was no internet as such. So we had to really travel, meet and talk to people in person, or ask for some kind of preprints to be mailed so that you can read that work. So that's so somehow the European part of the story is you know, my part of the story, and the American is the Canadian, and the US part is Charlie Bennett, Gilles Brassard, and Steve Wiesner, who should be given lots of credit here. And there were maybe other people who had similar ideas at some point, but I simply don't know about it, and nobody came up. So I'm sort of waving the flag saying, look, guys, I did it all before you did, but it was so secret that I couldn't publish it. I doubt it. Well, I think that you deserve coffee break. Thank you.